Assalamualaikum warahmatullahi wabarakatuh and greetings to each and every one of you. So now let's resume our course. We are still in food microbiology topic, so let's continue. In the last lecture, we have covered different types of microorganisms. Bacteria, fungi consist of yeast and mold, protozoa. We also have a parasite like cystoid and nematodes, a virus, a prion. So in this lecture, I'm going to go into more detail covering basic concept of microbiology. And for this lecture, most of the discussion will be comprised of bacteria because bacteria make up the majority of microorganism group. So I'm going to start with the first basic concept, which is microbial growth curve. So for this curve, what we are plotting here is number of microorganisms in the y-axis versus time in the x-axis. The unit of the time can be second or minute or also hours. Microbial growth curve are divided into 4 phases. First one is lag phase, the second one is exponential or we can call it log phase, the third one is stationary, and the last one is death phase. So basically this graph is telling you how microbes grow over time. A typical microbial growth will exhibit this trend of growth. Okay, let me start at the beginning. So we know that food is not sterile and there are microbes that are naturally present in the food. All the microbes can stay at a very low level if the food is stored properly. Or in other occasions, for example, if the food is contaminated with a spoilage microorganism or pathogens, there are maybe coming from contaminated water, maybe from a leakage roof from a processing environment, or maybe cross-contamination with other raw food. So the pathogen is adjusting to the food environment. If you're talking about the microbes that are present in the food, if you violated the maybe storage temperature of the food or relative humidity of the food, then those microbes that are naturally present on the food will be adjusting to that changes. How it's indicated in the growth over time is that in this phase there's no growth, so it's gonna stay flat, low level like this. After some time, for example, you left a cup of milk at ambient temperature, what's gonna happen is that the microbe will start to grow exponentially. It will increase to a very high level until the nutrients start depleting. When that's happened, the microbe is entering stationary phase, where the microbe growth rate is almost equal to microbial death rate. When the nutrient is continued depleting and the death of the microbe actually producing toxic material, what's going to happen is that all microbe will be starting to decreases and eventually die off, where this is actually describing the last phase of the microbial growth curve, which is the death phase. In microbiology, to inhibit the growth of undesirable bacteria such as spoilage microorganism and also pathogen, we are really focusing on the first 2 phases here, lag phase and also exponential phase. I'm gonna explain a little bit more about exponential or log phase in the following slide. Before I explain further about exponential growth, I'm going to touch a little bit about a standard written form how microbial population is expressed. It's usually expressed in the unit called CFU, colony forming unit. Why is it called that way? It's because usually bacteria is enumerated on a petri dish and then we'll see a colony on the plate. So that's basically what we count because we can see it from naked eyes. A table here basically showing you how arithmetic is converted into log 10 number. So basically this is a very simple math. I'm sure you can refresh your basic knowledge in math to understanding how arithmetic is converted into log number. So for example, let's say you have 150 CFU per gram bacteria and you want to convert it into log 10. So what you're going to do is that just get your calculator and then you plug in log and then whatever the number that you got. So in this case, it's 150. So the result from this calculation is 2.176 log 10 CFU per gram, or if you want to get the closest to decimal, it can be 2.18. So that's how it is converted into log. So this one is quite low number, 150, which is almost like in the 2 log range. What if you have a higher number of bacteria? Usually bacteria present at a very high number, especially in the environment that is so favorable for them to grow. Say you have a very large number like this and then you want to convert it into log. So same thing, you plug in all this number and then you will get this result, which is 8.3979 log 10, or you want to go to the closest to decimal point, which is 8.4 log 10 CFU per gram. So why CFU need to be converted into log CFU? Well, for the first reason is for simplicity. Because when you have a very high number like this, a lot of zeros, it can get really complex. So the microbiologists usually use log CFU to make the number look simple. So to go back to exponential growth, so this is basically what I meant. Bacteria is actually dividing in two, which result in doubling of the number from, for example, 2 to 4, 4 to 8, 8 to 16, to 32, and so on. It can grow exponentially depending on the environment they are in. So like I mentioned previously, usually bacteria present in a very high number, so using log CFU will make it more simple in terms of interpretation. So this figure really just showing you how bacteria is dividing, and then the specific term to call it is actually binary fission, where it's starting with one bacteria. It has to start at least with one bacteria and then it will go into 2, 2 into 4, 4 into 8, and so on. So the number of the generation, it actually represented by n here. Now I believe you already start seeing a trend, how bacteria is dividing, and also how much bacteria population it can produce from, for example, a single cell. So from this, we can actually obtain doubling time, which is another concept that refers to time needed for a bacteria population to double. So basically, the doubling time is represented by the arrow here. How much time does it need from a single bacteria to turn into 2 bacterial cells, from 2 to 4 bacterial cells? So it's represented by the arrow here. So if we understand this concept, now we can actually try to think a little bit more in terms of comparing the growth rate of the bacteria. For example, here's a quick comparison. Which bacteria has a faster growth? Is it bacteria A or bacteria B? What do you think? Right. If you think it's bacteria A, you're right, because the quicker it needs to double the population, that means the bacteria grow very fast. If the bacteria only double the population after 70 minutes, it just means that bacteria has a slower growth. Using doubling time concept, microbial growth actually can be expressed in a mathematical term, like I showed here. So the first one, basically just calculating a number of bacteria population after a given time. For example, if the food has a starting bacteria population like say 1 cell or 10 cell, and then after you leave it for some time, what is the total bacteria population? The next one is actually a formula for calculating the generation time. Well, these two is actually interrelated, which you will understand more with the example I'm going to show you in the next slide. Okay, here's an example. Let's say you have a fried chicken that you leave it at ambient temperature up until 5 hours. So this is how it will look like. Obviously you will not see the bacteria, but this is just for illustration. Say the initial population of the bacteria C, we call it C, was 100 CFU per gram. What is the total population of bacteria after 5 hours? So assuming that this bacteria C has a doubling time of 20 minutes. So here is how you calculate it. So make sure you convert it into a same unit. In this case, it's minute. So this is the time, 5 hours times 60 minutes, because 1 hour equal to 60 minutes. And then you divide it with 20, and then you got generation of 15. So basically, the bacteria have generated 15 times. So now we want to know the total bacteria population. So you just plug in the number. This is the initial bacteria population times 2 exponent the number of generation. So then you'll get this result. And then you want to bring it to the closest 2 decimal point. Then you got a final answer of 3.28 times 10 to the 6 CFU per gram. In this case, I don't convert it into log because it will be much simpler in terms of calculation. I don't want to confuse you with the unit conversion, but I want you to understand the purpose of this question, this example. Basically, this is represent food poisoning situation where certain food is left at ambient temperature, and then with that condition, the temperature optimal for most bacteria to grow, then bacteria can multiply, bacteria can grow on that food, and then reaching to a certain threshold that can be dangerous for the consumer. So briefly, to summarize the microbial growth curve, we know that food is not sterile. There are microbes that naturally present in the food, and then those microbes actually can cause spoilage. So what is the limit of those microbes to grow in such food? Considering that sometimes the temperature is little fluctuating, maybe the relative humidity is not as constant as we want to be. So in microbiological standard, most food should contain microorganism less than 10 to the 6. Above 10 to the 6 just indicate that those food need to be thrown away because it's unfit for consumption. When we talk about spoilage microorganism, it's actually represented in this column here. So we allow it to grow in a high number, however not exceeding 10 to the 6. Another column actually represent the coliform count. So what is coliform? Coliform basically is an indicator microorganism which basically tell us whether this food maybe experience some contamination. For example, if we talk about fecal coliform, meaning that the food can be contaminated by feces, maybe contaminated by contaminated water that contain feces. So that's basically coliform count. Well, E. coli is actually coliform. However, we know that not all E. coli is pathogenic. The one that we are only concerned usually E. coli 0157H7. So if we want to further investigate whether the food contain E. coli 0157H7, then we have to do further tests. Obviously, if it's pathogenic bacteria like E. coli 0157H7, then it should not present in food, like an example here. So in this type of food, for example, milk and ice cream, so E. coli 0157H7 shouldn't present here. So it has to be absent. In case for the testing showing that there's some number of E. coli, say 10 cells or even 1 cell, then the food need to be discarded, is unfit for consumption, because we don't want to introduce foodborne outbreak due to this contaminated food.